In this video, I'm going to be explaining the variation in air pressure and temperature with relation to the altitude. So I'm going to go ahead and write down some of the equations that we are going to need to solve this. At the end, we should hope to have one equation related to pressure and one equation related to temperature. Some of the equations we're going to need are the definition of static, so dP over dz equals negative rho g, where rho is the density of the gas. We're also going to be using this equation, du equals SQ, which is a small amount of change in heat, minus P1 dV. We're also going to be using the ideal gas law, which we know is PV equals nRT. But in this equation, well, in this problem, we're going to assume we have 1 mole of gas, so the N is just going to be 1. We're also going to be using two more small little equations. CV equals du over dt. There we go. And then also CP equals CV plus R, where in these two equations, CV equals the heat capacity as specific volume, and CP equals the heat capacity as specific pressure, and the R is the gas constant. So for the first part of the equation, we are going to try and solve for the density. So we're going to be using the definition of statics and the ideal gas law. So let's go ahead and do that. So I'm just going to rewrite this. dP over dz equals negative rho g. But for rho, what we're going to do is we're going to substitute in dP over dz equals negative mp, where the m is the molar mass, p is the pressure, g over rt. So this is our new equation. We're just substituting some stuff in. So from here, we're going to write it as T over P dP equals negative mg dz over r. From here, we want to take the integral of both sides. So let's go ahead and do that next. I guess we'll do that down here. And write the integral from P1 to P2 of T over P dP equals the integral from Z1 to Z2 negative mg over r dz. So we're going to leave the left side of this integral alone, and we're going to actually integrate the right side, and we're going to come back and use this later. So for our final step, we're going to have the integral from P1 to P2 of T over P dP, we're going to leave it just as it is, equals negative mg delta z over r. So we're going to need this later. I'm going to go ahead and box it in, and we will go solve for the next part. Alright, so in this next part, what we are going to try and do is get an equation that relates just to temperature. So for this, we're going to be using this equation, du equals SQ minus P dV. But we're also assuming in this problem that the system is adiabatic, which means the change in heat, which would be represented by SQ, would be 0. So let's rewrite this a little bit. We're going to write it as du equals 0 minus, and then we're going to sub in the pressure, so we're going to write it as RT over V dV. Okay, so right here, we're going to sub out the du. Let's zoom in a little bit, that'll help us. We're going to write it as CV dt equals negative RT over V dV. So this is what we have now. So let's do a little bit of rearranging. What's going on here? Oh no. There we go. Sorry, my OneNote's freaking out a little. Okay. So we're going to write it as CV, dt over t equals negative r dv over v. And so from here, we're going to take the integral of both these, and we're going to do some really fancy algebra. So we are going to write it as the integral. I don't really need to do that. So we'll write it as CV natural log from t2 to t1 equals negative r, and natural log from v2 to v1. There we go. Okay, so we're just gonna keep going. So the natural log from t2 t1 equals the natural log of v2 over v1, all raised to the power of negative r over cv. I keep going to get rid of the natural logs, which we'll do down here. And we'll write it as t over t1 equals v over v1 to the power of negative r over cv. So from here, we're going to get rid of the v's and write it in terms of r, t, and p. So we're going to write it as t over t1 equals rt over p rt1 over p1. This is still raised to the power of negative r over cv. But you can see here that the r's are going to cancel. The t's and the p's are not going to cancel though, because it's t1 and p1, not just either or. So let's do a little rewriting now. So we're going to do t over t1 equals t over t1 times p1 over p. Just do a little rearranging. It's still to the power of negative r over cv. But now we can see, since we have t over t1 and t over t1, we want to get those together. So we're going to do that as t over, oh my goodness, let's try that again. T over t1 to the power of r over cv plus 1. So that's just us doing the powers. Equals p over p1 to the power of r over cv. So from here, we're going to do a little definition. We know that r over cv plus 1 is equal to cp over cv, which is equal to gamma. So from now on, all of our exponents are going to be in relation to gamma instead of in relation to r and cv and plus and minus 1, because it's going to get a little confusing. So we're just going to go ahead and start calling it gamma. So let's rewrite this. T over t1 to the gamma equals p over p1 to the gamma minus 1. So the objective here is to get t by itself. So we're just going to keep going with the exponents. So we're going to write it as t over t1 equals p over p1 to the gamma minus 1 over gamma. And then the last step, we're just going to multiply the t1 over. So we're going to have t equals t1 times p over p1 to the gamma minus 1 over gamma. So this is what we were hoping to find, an equation just in relation to temperature. So let me zoom out so we can see what we were working with. So now, in the next step, what we're going to do is we're going to take this equation right here that we just found and we're going to plug it into the original equation that we found to find an equation that relates to pressure. Alright, we'll do that in the next step. Alright, so we're just going to go ahead and plug those things in directly. So I'm just going to start writing the integral from P1 to P2, and then we're going to go ahead and substitute that in. So we're going to write it as T1 P over P1 to the gamma minus 1 over gamma all over P dP. So that's just subbing in what we got in the last two parts, equals negative mg delta z over r. So we're going to pull out our constants. I'm going to pull out T1 and P1 to the power of 1 minus gamma over gamma, because we're pulling that out. Integral P1 to P2 of P to the gamma minus 1 over gamma dP. And then it's still equal to negative mg delta z over r. So we're going to go ahead and put all the constants together on one side and then the integral on the left. So we're going to move the t's and the p1s over to the right side. So let's go do that over here. We're just going to have the integral from p1 to p2. Nothing's changing over here, of p to the gamma minus 1 over gamma, dP, equals negative mg delta z over r T1 P1 to the gamma minus 1 over gamma. And again, the power changes because of the multiplying and dividing across. So now we're going to actually solve for the integral, and it's going to be p to the gamma minus 1 over gamma minus 1 over gamma from P1 to P2. So we're going to rewrite that as P2 gamma minus 1 over gamma minus P1 gamma minus 1 over gamma all over gamma minus 1 over gamma. And everything on the right stays the same, so we're still going to have minus mg delta z over r T1 times P1 to the gamma minus 1 over gamma. So from here, we're going to multiply this across, and then we're trying to solve for P2 by itself. That's the objective here. So we're getting close. We're going to have P2 to the gamma minus 1 over gamma minus P1 to the gamma minus 1 over gamma equals negative mg delta z r T1 times P1 to the gamma minus 1 over gamma. Let me put these in parentheses so you can see that a little better. And then we're multiplying it by gamma minus 1 over gamma. So we just are making that a little simpler. So now we can see that on the left and on the right we have terms that have P1 to the gamma minus 1 over gamma. So we're going to go ahead and get those together. So we're going to write this as P2 to the gamma minus 1 over gamma equals P1 to the gamma minus 1 over gamma 1 minus all the same stuff, g delta z over r, sort of looks like an r, T1, and then gamma minus 1 over gamma. So that is what we're working with now. So we're on our final step. We just have to pull out the exponent. So we're going to do that down here. P2 equals P1, 1 minus negative mg delta z over r T1 times gamma minus 1 over gamma And all of that is to the power of gamma minus 1 over gamma. Perfect. This is what we were trying to find. So this is our one equation that relates to pressure. Now from here, we're on our final step. We're going to go ahead and find the equation that relates to temperature. So from before, we remember T equals T1 P over P1 to the gamma minus 1 over gamma. So from here, we're just going to have that T equals T1. It's going to be the same kind of stuff. 1 minus negative mg delta z r over T1 times gamma minus 1 over gamma, but this one's not raised to the power. So this is the final equation for the temperature. We have the final equation for the temperature, the final equation for the pressure, which is what we were hoping to find, and they're both related to the altitude, which is the dz. So all of these other things are constant except for the dz. That's the only thing that's changing. So we have officially found how the pressure and the temperature relate in relation to the altitude. Thank you.